Hello, and today we're going to be looking at the observable universe. I may come off a little down right now because I just watched Hachiko, a true story, and I'm currently reading the children's book to write a unit plan on it, and I've just been crying all day. I love dogs, which is a really sad story, but we're going to go on and we're going to look into the observable universe. We're mainly going to be looking at the spectrum of light in terms of a Doppler effect and what that says about the distance of brilliant spheres or stars or other planetary objects that reflect or refract light relative to our position in the universe. So I found this neat little picture on the internet that basically states what our universe would look like if it was all in one sphere. It's kind of interesting how our solar system's the center of it, but we're not the center of the universe, but it's a neat depiction. So I put it up here. So for our Doppler effect when it comes to light, first we have to understand exactly what we're looking at. So what we're looking at are the remains of elements, because all matter exhibits a wavelength. So what you measure is the light that passes through matter, and it kind of comes through in this barcode manner. So you can see that the different colors of light as they pass through matter exhibit these barcodes that says about the distance and or composition of that matter. So for an example, the presence of red lines indicate farther matter, so stars that are farther out will have a red color to them when we try to measure their distance, and blacker, thicker lines can indicate how light passes through certain elements. And of course, the wavelength spectrum, as we can see here, goes from red. It actually goes from red to white being the brightest, but for here it goes to purple. Because white light is the combination of all the colors. Red is the lowest wavelength, and these will indicate the distance of stars from us, somewhere on the spectrum. The closer it is to blue, the closer it is to us, relatively speaking, and the closer it is to red, the farther it is from us. The spectrum of light comes from white light, which is composed of many colors, from red to violet. So think of sunlight being refracted through a prism, as this background image shows. And the black lines are what we would call emission line spectrum, so gas absorbing light, resulting in different wavelength patterns because, as stated before, matter does have its own wavelength. Light passing through matter also has a very unique pattern to it. It tells us the composition of gas in distant stars, so helium, hydrogen, gases that are primarily in stars. And the colors also depend on the relative motion to us of the source and the observer. So think of the theory of relativity, where time is observed differently dependent on the observer and the event being identified. And just a fun little side note, I'm a Hindu. I converted a few years ago, and I study a lot of the yogas and Reiki and a lot of spiritual sciences along with it. And something that comes up continuously when it talks about purifying our bodies of negative energy is the 7 chakras, which are energy nodes within the body that go from the genitals up to the top of the head. And there are a few sub-chakras, which I'm not going to get into, but the main 7 ones were described thousands of years ago before the science of the composition of light and spectral analysis of stars came into existence. And I think it's really interesting that those same chakras, starting from red being lowest to violet being the highest, share the same color wavelengths. And it really says a lot how the energy of the stars is within us. And I'm going to discuss red shifted versus blue shifted now. And as I said, the red shift is a longer wavelength. I know in another video I spoke about wavelengths. The longer the wavelength, the more space there is between the ups and downs of that wave, so that's farther from us. And a blue shift is a shorter wavelength, such as a short wavelength would have waves more squished together. It's blue in color, or closer to blue at least, and it's closer to us. And you can think of this as a kind of Doppler effect, but with stars instead of like waves here on Earth. And the Doppler, perhaps I didn't go too into it, but the Doppler effect is basically measuring the wavelength of energy as it encounters an object. So, for example, if you toss a rock in a pond, it has that ripple effect, and that's essentially what the Doppler effect is for things here on Earth. And I did kind of mess up the formulas here because I cannot find this particular symbol. It looks like an upside down Y. One part came out black. I tried making it myself, but this is the basic gist of these formulas. So delta, this little triangle, is delta observed wavelength over a baseline wavelength that's relative to our own experimental replications on Earth, equals velocity over speed of light. And the baseline right here is the second formula. So delta light observed over a baseline. The baseline is light by 0 minus light. I'm so bummed out from that movie. And then, of course, this will equal velocity over c. So it's velocity over light, the speed and direction of light. So the direction that light is coming to us from. And this is a formula again, we still have these terms of delta and the relativity of the light, where it comes from. It's red shifted or blue shifted. And again, z is going to equal velocity over speed of light. And again, keep things relative. It's relative to our position here on Earth, and depending on Earth's orbital activity around the sun, the different parts of the cosmos we are viewing at the moment. Distances are also considered, we use stars mainly to measure distance, so supernovas, for example, which are extremely bright. But they're measured by their parallax, which is the observed movements relative to their background. So what we're seeing distant in the background compared to what we're seeing from them. And this would also define the astrological unit of distance, which is a parsec. So you have to think of it within degrees. You know how the Earth tilts on its axis at a certain degree? Well, stars would have a similar motion. So it's 1 minute by angle of 5 degrees. So think of it like that. And we use this with standard candles, mainly with supernovas. Standard candles are a way of measuring this, and so we're measuring the luminosity of star and light. The star or light source to measure the distance, which is B equals L over 4 times pi times D squared, which is brightness as it decreases to us, which would equal light per second over the sphere. This formula here is for the sphere, and this is for light. And sphere is very important here because when we speak of celestial spheres or planetary bodies, it will typically be in that shape. You can't encounter a planet that is like a square. And that's the end of the PowerPoint. So this is important mainly because we need light to measure distances in the universe, because we perceive things through the form of waves, whether they're electromagnetic or physical, like clapping my hands produces a wave, a sound wave. There's no sound in space, so we're left with light. And thus far, our observable universe is what we can see. Other things in the universe, such as dark matter, we have to use our best mathematical estimates and calculations to make up for the rest of the density. This would give us, with what we've observed, just on a standard level, like with standard candles, for example, which are supernovas, we can kind of determine how much matter is out there in the universe and what planets potentially are habitable. And this would also speak to the critical density, so how much matter is in the universe and how that would actually affect us. So if we're at perfect equilibrium, we're in a flat universe, which I'll go to another video. I did speak in the previous video about a Euclidean plane and us having a flat universe. That would mean we're at the perfect density. Negative density would mean that our universe is going to crunch in on itself, and a positive one would be that's going to expand and then possibly explode. I'm more concerned with negative density and the density we have now. So it would be either equal to 1, more than 1, or less than 1. So yeah, that's pretty much it for the observable universe. So yeah. That movie really bummed me out. I'm so sad right now. Don't watch sad movies before you